Let's continue and discuss a little bit about spectroscopy. Now, we know that spectroscopy is the interaction of light with matter, and we've got a couple of options. Either the light can go in with this, which is absorption. Imagine your car getting warm on a hot sunny day, or light can be emitted, so light can go out. And when light goes out, it is instead emission. Now, absorption would be X-ray. Emission would be, for example, what you would see from neon lights or fireworks are great examples of emission spectrums. Now we got two options on these. We have either line or we have continuous. And we're going to consider both of those. Neon lights that we see are an example of an emission spectrum. The different colors are produced by chemicals that they have on the inside of the lights themselves, and this is an example of a line spectrum. And we'll see what that is in just a sec. All right, so looking at types of spectrum, continuous is an example of white light. This is what we would see if we look out the window and we look at the sun. It is continuous in that there are no separations and there are no missing colors. In comparison, these guys are all line spectrum. Line comes from the fact that if we take the light that comes emitted from one of these elements and we put it through a prism and shine it on a photographic plate, it comes into lines of color. And these lines of color are what we see when we look at, for example, hydrogen being emitted, or light from the hydrogen atom being emitted if we put energy into hydrogen. So line spectrum, continuous spectrum. Niels Bohr tried to explain this. He tried to explain the fact that if we consider an element, and we're going to start with hydrogen, because hydrogen is by far the simplest, we have one proton and we have one electron, and he tried to explain the structure of the atom using the colors and the type of light that are emitted from them. And here's what he said. He said that we have a nucleus, and that is our proton, and that around the nucleus, the electron can exist in orbits, orbiting like a planet around the sun. Now, as this electron can exist in orbits, so this would be the first orbit, and the second and the third, so we can imagine it as the nucleus. This is first orbit. The second orbit might be out here somewhere. And then the third after that, assuming I can draw here, and that the electron can exist in any one of these, because this again is hydrogen. It's got one proton and one electron, and this electron, unlike our planets, can bounce in between these orbits. It can go from orbit 1 to 2, or let's say 1 to 3, and when it does this, it emits light. If it goes up, it's going to absorb. If it goes again from here to here, this is absorption. If it goes from the outside and goes in, it is going to lose energy, and energy is going to be emitted, and it's going to be emitted as light. And this energy and the colors, so remember that energy is proportional to our frequency, which means the energy depends on color. And so therefore, if the color and the colors on these guys are fixed, then these energies are fixed, meaning certain energies, which means that the orbits themselves are fixed. And this is the Bohr model of the hydrogen atom. So, Bohr model of the hydrogen atom. We have a nucleus. Now the nucleus just has to contain protons, some number. If we have hydrogen as one proton, the key on this, it can have any number of protons, but it can only have one electron. So it could have two protons and one electron. If it has more than one electron, it becomes a very complicated mathematical problem. So let's say we have here our hydrogen, one proton, one electron. The electron can exist in these orbitals. If it's in the closest orbital to the nucleus, it's called the ground state. And any orbital above that is a higher energy. And so 2, 3, and above would be an excited state. Our excited states are unstable, and if our electron ends up in one of the excited states, it is going to go back down again to a lower state, and it's going to emit energy. And it's going to emit energy such that our delta E, our change in energy, is equal to Planck's constant multiplied by the frequency. There are quite a few equations that we can use for the Bohr model. Now, he simply made this assumption. He said that the electron exists in fixed orbits around the nucleus, that this electron can go back and forth between these different orbitals, or orbits, excuse me, not orbitals. If it goes up from a lower to a higher orbital, energy is absorbed. If it goes down from a higher to a lower, energy is emitted. We have quantum numbers, numbers that describe the orbitals. The closest is n equals 1. The furthest out is going to be n equals infinity. And our equation is that the change in energy is equal to a constant multiplied by 1 over n sub f squared, which is the final, minus 1 over n sub I squared, where it's got a negative sign. And it's got a negative sign because we have energy issues. If energy comes out, it is going to be exothermic, and it's going to have a negative value. And if energy goes in and it's being absorbed, it is going to be endothermic, and our energy is going to be positive. And we can plug in and we can solve for things. Personally, I hate this equation. I'm going to use a shorter one. So instead, I'm going to use a different form, and I'm going to use 1 over lambda is equal to the Rydberg constant multiplied by 1 over the n inner squared minus 1 over the n outer squared. Why? Because this is going to solve for wavelength. We can always convert from wavelength into energy because we know that E is equal to NhC over lambda, and this removes the sign. If we have no sign on here, this is always going to be positive. Wavelength is never negative. It doesn't matter if it goes one direction or the other. N sub I is the inner, and this is the smaller n. N sub O is the outer, and this is the larger value of n. So let's plug through that in the next question. All right, using my favorite form of the Rydberg or the hydrogen equation, we're going to have 1 over the wavelength. It is the Bohr model. The equation is frequently called the Rydberg equation instead, is equal to this R times 1 over n sub I squared minus 1 over n sub O squared. Using meters for the unit in our wavelength, our R value is equal to 1.097 times 10 to the 7th units of per meter. So that's what I'm going to do. 1 over the wavelength is equal to the R. 1.097 times 10 to the 7th per meter times lower value, 1 over 2 squared minus 1 over 3 squared. This is just math. Take and combine all of this, and you're going to get that 1 over the wavelength is equal to 1.52 times 10 to the 6th units of per meter. Now, if I want to solve for this, I've got to get lambda, or the wavelength, by itself. So I need to do wavelength is equal to 1 divided by 1.52 times 10 to the 6th per meter, and I will get 6.58 times 10 to the minus 7 meters. If I put this into nanometers, I'm going to get 658 nanometers, which is the red line from the hydrogen atom. Equally, you can use the value where you're looking at the Rydberg constant, or R, 2.18 times 10 to the minus 18, and get your energy for this instead. I'm simply going straight to wavelength. So, how does this work? Well, first of all, this works fantastic. If we have hydrogen, this equation perfectly, and I mean perfectly, gave us every wavelength or every color that hydrogen emits or absorbs. Okay, gives us them all. So our equation works great for hydrogen. It also works for helium with +1 or lithium with +2 and nothing else. So it only works for one electron atoms. And we've got another problem. And our problem is if we have our nucleus, which is positive, and we have our electron sitting here in fixed orbits, the electron is negative, the nucleus is positive, and this electron should just swing down or spiral down and stick to the nucleus. Opposites attract. So, a couple of issues. One, the original assumption is ridiculous. And two, it only works for pretty much hydrogen. So, after all of that, we need a new theory because this one doesn't work. So the first thing I want you to walk out with this is don't think about the atom as having the nucleus here with the electron in orbit. It only works pretty much for hydrogen.